Alright, so problem number 3 is a good old-fashioned mass on an incline problem. So the problem reads, a mass m slides down a frictionless incline that has angle theta with respect to the horizontal. A asks, in terms of m, theta, and any applicable constants, calculate the amount of the mass's acceleration down the incline. So, I use, first of all, our equation, acceleration equals sum of forces over mass. Okay, so a couple things to know. So I drew this free body diagram of the mass on the incline, and because the slope of the incline is not horizontal to the ground, I offset it a little bit and made it straight. So we have the normal force upwards on the mass in this direction, and then we have a gravitational force in this direction on the mass. So it's really in this direction with respect to the incline. So because the mass is not accelerating vertically with respect to the actual incline itself, I know that the normal force and the vertical component of the gravity force are canceling each other out, so what is accelerating the mass is the horizontal component of the gravitational force, which is this one right here. So using some trig, I find that that force is equal to Fg sine theta. So I have Fg sine theta over m, and that's my acceleration. So part B reads, if the mass starts at rest, calculate how much time the mass takes to slide a length L down the incline in terms of m, theta, L, and any applicable constants. So I have constant acceleration here. So I'm going to write out my givens. V1 equals 0. I'm looking for delta t. Acceleration I just found, and delta x equals L. So I'm going to have delta x equals v1 delta t, which is equal to 0 because v1 equals 0, so I can cross it out all the way down, plus 1/2 a delta t squared. So in order to find delta t, I'm going to need to use quadratic. So I use that, and then I end up with my final answer as square root of 2 Fg sine theta L all over Fg sine theta. And that is the amount of time the mass takes to slide a length L down the incline. Somewhere where students might get stuck on this problem is writing a free body diagram on a slope like this one. So something that really helped me was to just draw the axes like I did and offset them a little bit with respect to the actual incline, and then draw the forces in and even the components if you want off of these axes. Of course, I wrote down equations that I thought I might need. And so yeah, that's one thing that helps with the problem a lot and somewhere where students might get stuck. So